Hi, this is Math 2520, and this video is the third part to Chapter 11. In the second part, we had looked at the Taylor series and introduced it and did a couple of examples. We also believe compared it to the Maclaurin series, which is centered at 0, or the Taylor series is centered at another number like A. We just call it A, but it's centered at something other than 0. For the binomial series, alright, so we can find the Maclaurin series for a function f of x equaling 1 plus x to the k, where k is any real number. In doing so, we must determine the nth derivative for n equals 0, 1, 2, and 3. And what we get from that is called a binomial series. For any real number k, the absolute value of x less than 1, then 1 plus x to the k is 1 plus kx plus k times k minus 1 over 2 factorial x squared plus k times k minus 1 k minus 2 over 3 factorial x to the third, and that's because the power comes down in front of these. And so at the end of the day, it's going to equal summation n equals 1 to infinity of k factorial over n factorial k minus n factorial x to the n minus the summation of n equals 0 to infinity of k over n x to the n. Each coefficient can be written as this is just kn, not k over n. Each coefficient can be written as k over n being k factorial over n factorial times k minus n factorial, which are called the binomial coefficients. And so we must check the convergence at x equals plus and minus 1, and the convergence depends on k. So it converges at 1 if negative 1 is less than k, which is less than or equal to 0, and at plus negative 1 if k is greater than or equal to 0. Alright, so we want to find the first 4 terms of the Maclaurin series for the function f of x equaling the square root of 1 plus x, and use it to approximate square root of 1.17. Right, so we're looking at here k equaling 1/2 because of the square root. That's your power. So summation from n equals 0 to n of 1/2 3 x to the n. That's going to be 1 plus 1/2 x plus 1/2 times negative 1/2 2x squared plus 1/2 times negative 1/2 times negative 3/2 x cubed over 6. And so that's first 4 times 1, 2, 3, 4. And so we'll do some simplifying here. 1 plus 1/2 x. This is going to be minus 1/8 x squared plus, and that'll be 2 times 2 times 2, and then 3 and the 6 cancel out. I'll write that in. 3 cancels with that, so it'll be another 2, and so you'll be 1/16, and the 2 negatives can get positive, and that'll be x to the third. Okay. So with this, then you'll have for the approximation of square root of 1.17, you'll have 1 plus 1/2 0.17 minus 1/8 0.17 squared plus 1/16 0.17 cubed, and that's going to give you roughly 1.082. Okay. Actual is square root of 1.17 equaling 1.081063. Okay, so it's really close. Okay, it's not correct at the fourth term, but it's close, very close. Okay. Now, you can always derive a Maclaurin series, but often it's quicker if you can memorize a few common ones. And so here are some common ones to memorize. And the radius of convergence. So 1 over 1 minus x, radius is 1. And your series looks like expanded out 1 plus x squared plus x cubed and so forth. Right. E to the x, radius is infinity. And so your series expanded out would be 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 over 4 factorial and so on. Right. Sine of x, radius of convergence is infinity. And you have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. So it's just all the odd terms. Cosine, 1 plus or 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. So it's all even terms, and then these alternate signs. Right, I'm not going to go through all of them because you can read them, but we're going to do a couple examples. Find the sum of the series. 1 plus natural log of 2 plus natural log of 2 squared over 2 factorial plus natural log of 2 cubed over 3 factorial. Okay, so we can write this as the natural log of 2 to the n over n factorial. And if we notice, if we expand this out, it's this particular one will have here 1 plus natural log of 2, and natural log of 2 squared over 2 factorial, natural log of 3 squared over 3 factorial. So we're looking at this second one, okay, which comes down to the function e to the x. So we're looking at e to the natural log of 2, which is going to be equal to 2. This next one, we can write this. Notice it alternates sign, and then you have a natural log of 2 that's being taken to the nth power, and then n is also in your denominator, n factorial, that is. And since both the negative sign and the sign are being taken, we can put that into 1. Negative natural log of 2, n power over n factorial. Okay. So again, it looks as the same particular series we have again, the second one. And so we can write this as e to negative natural log of 2 which is going to be e to natural log of 2 raised to the negative first, which ends up being equal to 2 to the negative first, which is going to be equal to 1/2. Alright, so next couple of examples. Find the Maclaurin series for f of x equaling sine of 2x and g of x equaling x sine of 2x. Alright, so we'll start with what sine of x is. Where is it? So summation from n equals 0 to infinity, negative 1 to the nth, x to the 2n plus 1, I want to make sure I wrote that right, over 2n plus 1 factorial. So sine of 2x, summation a equals 0 to infinity, will be negative 1 to the n. That doesn't change. X is what's changing. 2x to the 2n plus 1 over 2n plus 1 factorial. And then we can write this as summation n equals 0 to infinity, negative 1 to the n, 2 to the 2n plus 1, x to the 2n plus 1 over 2n plus 1 factorial. And then x sine of 2x will be x times the summation of n equals 0 to infinity of negative 1 to infinity, 2 to the 2n plus 1, x to the 2n plus 1 over 2n plus 1 factorial. Okay. And so we'll bring the x in. And so when I do that, I'll have x times x to the 2n plus 1. And this will be basically x to the 2n plus 2, which is x to the 2n plus 1. So that's what that's going to be at the top. Over 2n plus 1 factorial. Okay. So the two answers we have, this is for sine of 2x, and then this is for x sine of 2x. Alright. Find the first four non-zero terms of Maclaurin series for arctangent x e to the x. Alright, so arctangent x is x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and so on. Again, this comes from the table. And the e to the x, again from the table, it's 1 plus x over 1 factorial. I'll write that in. X squared over 2 factorial plus x cubed over 3 factorial, and so on. Okay, so we're doing arctangent x e to the x. then we have to kind of multiply these together. So x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 times and dot 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 1 plus x squared over 2 factor 2. Let's keep that number, plus x cubed over 3 factorial and dot dot dot. Oops, did not mean to change the color like that. Okay. So when we multiply these terms out, we'll get, x times 1 is x. Remember, we want to go by powers too. So constant term, that won't be a constant term. Next term would be x power. Next term would be x squared, so x times x squared, or x is x squared. So that's this one times this one times that one. The next one you'll get will be x cubed, and we'll have two of them. We'll have minus x cubed over 3 times 1, and x times x squared over 2. Right, and so minus x cubed over 3 times 1 plus x cubed over 2. Right, and they will have to go together. I'll find the sum here soon. And then we go beyond that. We gotta look for the fourth terms. There's no x to the 4th on this side, but if we take that x cubed over 3 times x, we get negative x to the 4th over 3. And then we take x times x cubed over 3 factorial, we'll get plus x to the 4th over 3 factorial. Okay, and dot dot dot. So x plus x cubed. And then we'll find common denominator here, so 2/6, and this will be times 3, 3, 6. So we'll get just 3 minus 2 would be 1, so plus x cubed over 6. And then here, 3 factorial is 6. And this will be 2/6. And so we'll end up with negative 2 minus 1 would be a minus x to the 4th over 6. And so these are the so these are the first 4 terms. Alright, so application problems now for Taylor-Maclaurin series. First one, in wildlife conservation area, population of certain endangered species is growing according to the following function. P of t is the population, t in years, t equals 0 represents the start of the population study. The exponential term e to the negative 0.1 t is difficult to compute, mainly for small values of t. So to simplify calculations for early years, the population biologist decides to use a Taylor series and the expansion of e to negative 0.1 t around t equals 0. Right, so we'll find the expansion series for e to the negative 0.1 t. Okay, so remember for the Taylor series, it's f of 0 plus f prime of a times x minus a over 1 factorial plus f double prime of a times x minus a squared over 2 factorial, which is 2, plus f triple prime of a times x minus a cubed over 3 factorial, which is 6. And then we're going to look at this for our specific term e to the negative 0.1 t. So when t is 0, you get just e to the 0. And then the derivative of this is a negative 0.1 e to the negative 0.1 t. And we're doing this at 0, so we'll have just x is, we'll use t in place of x, so t minus 0 will be t. And then second derivative, 0.1 squared e to negative 0.1 t times t minus 0 squared, which is just t squared over 2, plus a negative 0.1 cubed e to the negative 0.1 t times t cubed over 6. I didn't include something, I'll do in one more step, but t in all these that are e to the, I'm sorry, all these functions here is evaluated at a. So I wrote it with the t in there. I'm supposed to put a, and a is 0, so they're all e to the 0, which is just 1. So this is going to be 1 plus a negative 0.1. E to the 0 is just 1 times t. Plus 0.1 squared, t squared over 2, plus 0.1 cubed, t cubed over 6. Right, so now we can write this as population function as 1000 over 1 plus 9 times 1 minus 0.1 t plus 0.1 squared t squared over 2 minus 0.1 cubed t cubed over 6. Alright, so now the next question is we want to estimate the population at t equals 2. Alright, so we'll find p of 2. It's going to be 1000 over 1 plus 9 times 1 minus 0.1 times 2 plus 0.1 squared times 2 squared over 2 minus 0.1 cubed times 2 cubed over 6. And so this is 1000. We'll have 1 plus, as we distribute the 9, you'll have 1 plus 9, which is 10. And then minus 9 times 0.2. Plus 9 times, and so this 2 will cancel with that, so you have the 0.1 squared times 2, right, and then 9 times this, which 2 1/3 is 8. Some things will cancel down. I'm just going to write out 9 times 0.1 cubed. 8 over 6 be 4 over 3. And the 3's cancel with the 9, but I won't do that till later. So 4 over 3. And then we can put all this into a calculator. What we end up with, and remember all this is underneath that denominator, you end up with 1,000 over 8.368, which ends up being about 119.47. So you can just plugging that stuff into a calculator. Okay, so that's the estimate. As soon as it saves, we're going to look at the actual, and that's just using the formula. So P of 2 is 1,000 over 1 plus 9 e to the negative 0.12. Right. And if you put this in a calculator, you get roughly 119.49. And so your error here is 119.49 minus 119.47, which is 0.02. I'm taking the absolute value, so it doesn't matter which one goes first there. You're about 0.02 off then. Next one, we're going to use the Maclaurin series. Company is developing a new product and has modeled a production cost as a function of number of units produced, C of X, where X is the number of units and the cost is C of X. And it's given by the formula 100 plus 50 e to 0.05x. However, for small values of x, when production is just starting, the company wants to estimate the cost more easily by using the Maclaurin series. And so we do expansion for e to the 0.05x. So for the Maclaurin series, you have f of 0 plus f prime of 0, 1 factorial, plus f prime of 0, x squared, 2 factorial, plus, and so on. And so for e to the 0.5x, we are looking at e to the 0 plus 0.05 e to the 0 over 1 plus 0.05 squared e to the 0 over 2 x squared. I forgot the x here. And so e to the 0 is just 1, so you get 1 plus 0.05x plus 0.05 squared x squared over 2. So to use this series, C of x, do 100 plus 50 times 1 plus 0.05x plus 0.05 squared x squared over 2. And so we'll distribute that 50, 100 plus 50, so we'll just make that 150, plus 50 times 0.05, which is 2.5 x, and 50 times 0.05 squared over 2, which ends up being 0.0625 x squared. So if we estimate the cost producing 1,000 units, x equaling 1, using the Maclaurin series approximation. So we'll find C of 1, which is 150 plus 2.5 times 1 plus 0.0625 1 squared. So we get 150 plus 2.5 plus 0.0625. And so we end up with 152.5625. And when we look at the actual cost, C of 1 is 100 plus 50 e to the 0.05 times 1, which is 152.5636. So the error here is equal to 0.0011. Okay. Alright, I'm going to finish this chapter out. We only have a couple pages left. Alright, so why is it useful to use a Taylor polynomial to approximate functions? I recall sometimes we have functions that aren't derivatives of nice functions. These are called non-elementary functions. Some include examples like elliptical integrals, integral of natural log, e to the x over x, and so on. Some of these functions do come up in an application, so not being able to calculate them can be a problem, and so that's why we will use Taylor polynomials. I have taken a couple classes that deal with difficult mathematics, and usually that's what we do is end up using some kind of Taylor series or some kind of other series to find a solution. Alright, so let's look at f of x equaling e to the negative x squared. The integral of e to the negative x squared does not exist. So to actually find a summation here, we're going to represent this as a Taylor series. So the Taylor series for this going from I'll use n going from 0 to infinity, or e to negative x squared times 0 over n factorial times x minus a, or the nth power. Now, where's the table? Which is following our e to the x here. So infinite series is not always practical to use for approximation, so instead we use Taylor polynomial and so many coefficients. We can see any function within a certain radius of conversions of the power series with appropriate choice of coefficients. We can see the radius of conversion. So if we look at the graph below, first one is sine of x, the blue one is f of x equaling x, then we have x minus x cubed over 3 factorial is your green one. So green one, notice it kind of goes in line right here with the blue one, goes in line right here, and this red one also same area, it's overlapping. Trying to get purple. There we go. Purple one right here overlaps as well. And then the other red one, I didn't realize we used two reds also, and will overlap. So that there's a section here, right here, yellow, yellow, that all of these are overlapping. So for right around that small area where they're converging, that's where these series approximate, or a good approximation to the function. So as n increases, the Taylor series becomes a good, better approximation. So they're all overlapping there, but what you're also noticing, or you would notice, is that from the as you increase farther down, so the first one is X, you have the smallest overlap. Right. The third one, let's go to the purple one. The purple one has a much larger overlap. Right? It overlaps from here to here. And then the other red one has an even bigger overlap. I kind of started doing that when I was drawing it. I drew it more farther out each time. And so as n increases in terms, this one has more terms than this one, you have a better approximation. Alright, so the last thing. Naturally, if we cut off the Taylor series at n equals 100, we are missing terms and we'll not get an exact solution. The sum of the missing terms is called the remainder of the Taylor series, and we denote this as R of n of x, or you can think of it as the error. Then we can write the Taylor series plus your R of n of x. Alright, so for Taylor inequality, if f to the n plus 1 of x is less than or equal to 1 for x minus a less than d, then the R of n of x is less than or equal to m over n plus 1 factorial, x minus a in absolute value, n plus 1. And this again is for x minus a less than d. So we want to find the maximum error in approximating cosine of 0.4 using the 10th degree Maclaurin series. So we're going to look at a equals 0. So we'll have R of n of x less than or equal to 1 of n plus 1 factorial to x minus a n plus 1, which is going to be less than or equal to 1 over this 10th degree, so 10 plus 1 factorial over x minus 0, 10 plus 1, which is going to be less than or equal to 1 over 11 factorial, is absolute value of x to 11th, and then that'd be less than or equal to 1 over 11 factorial, 0.4 to 11th power, and that comes out to be approximately 1.5 times 10 to the negative 12th. Alright, so that is the end of chapter 11. The next chapter will be chapter 12, and we'll get into parametric equations, which deals with a lot of times x and y both being linked to a time variable. Alright, I'll see you then. Bye.